Okay, everybody thawed out, more or less. Goes without saying today, obviously, spend as little time outside as possible. If you can, cover your face. If there's any white patches that you can't feel, that's not a good thing. All right, stay warm, stay safe today. Okay, let's talk about robots. We are going to finish our theme on the tools of the trade today. We've talked a little bit about artificial neural networks, which are going to serve as the brains of our robots. We talked about a series of evolutionary algorithms last time, where we started with very simple algorithms, which were weak learners. They tended to get trapped in local optima or the various hills of a fitness landscape. And we marched through a series of increasingly sophisticated evolutionary algorithms that became more algorithmically complex. And we justified that complexity by their ability to escape from local optima and continue searching for the global optima, the best possible solution to our given problem. As I mentioned last time, however, all evolutionary algorithms share one limitation in common, at least at the moment, which is that we cannot guarantee that we've ever found the global optima, or global optimum. Why not?
Because you don't have the entire topography.
The fitness landscape.
You don't have the entire fitness landscape available to you. You just have the points that you pick.
Exactly, right? So we visualized schematically last time the fitness landscape, which is this surface where any horizontal position in the fitness landscape represents one possible solution to our problem, and the height of that point represents its fitness or its quality or how good that solution does at solving the problem. But the problem, the real problem, is for any given problem, we don't know what that fitness landscape looks like. If we did, you could simply go to that point in the landscape that's highest and we're done, right? We're using an evolutionary algorithm or any machine learning algorithm. What it's really doing is trying its best, given the computational resources we make available to that algorithm, to search that space as efficiently as possible and find the highest or the lowest, depending on how we define fitness or quality, in that space as possible. And as we continue on with the course, we're going to look at a large number of experiments that use different kinds of evolutionary algorithms. I don't expect you to remember the details of all the different evolutionary algorithms we see, but I want you to think about when we talk about a particular application and a particular evolutionary algorithm, what are the pros and cons of that approach? Can you think of a way of altering the evolutionary algorithm that the investigators might have done a better job at finding a controller for their robot to do whatever they wanted that robot to do? Okay, we're going to move on today to physical simulation. Obviously, we're not working with physical robots in this class. We're going to be simulating virtual robots that exist in a virtual environment. What is that actual virtual environment? What is going on when you simulate a robot in a physics engine? We'll talk about that today. The reading for today comes from the Open Dynamics Engine, or ODE, user guide. And ODE is the physics engine that you're using, and it is wrapped inside a PyroSim. So PyroSim, the Python library that you're going to be using for most of the work in this course, is basically a Python wrapper around ODE. So what does that look like? Well, when you create your code and you import PyroSim and you create an instance of the simulator and you start up that simulator, that creates a call and starts up a piece of C++ code. And inside that C++ code is one giant loop that repeats a pre-specified number of times. And every time this C code iterates through this loop, it updates or simulates one short instant of time in your virtual environment. And we're going to talk about today what happens during this loop. After this loop is iterated however many times you want, the default is 1,000 time steps. This system will return S sensor data to you. So as the robot is moving about in its environment, it is simulating, as the robot is moving through its environment, the environment is being simulated, the robot is experiencing 1,000 instants of time, which are the 1,000 iterations through the physics engine, and we're going to get back either a vector of 1,000 numbers, or if the robot has more than one sensor, we're going to have S by 1,000 values coming back, and that is collected by sim.wait to finish. So in essence, when you're running your code here, you're actually starting up two processes running on your machine. The first process is your Python code. When you execute start, your program counter, your program pointer, your program continues on to whatever lines follow start. And there are things that you can do between here and here if you like, and we'll talk about that later. But if your program continues and gets to wait to finish, and the simulation has not yet finished, then it will, as the name implies, it will wait for your C code to finish and then collect the sensor data back. So far, so good?
Why did you implement a Python wrapper? What's the advantage of having a wrapper versus just running everything from C++?
What's the advantage of having a Python wrapper rather than having you access the C++ directly? How many of you code in C++? Quite a few of you, that's pretty good. Okay, in previous years, we had students actually go in and work on the C++ side itself. If you're interested in physical simulation, by all means, be my guest. You can go in and have a look at what's actually going on under the hood. What the PyroSim Python wrapper does is allow you to focus on robotics, and we'll talk about that today. You can really focus on the robotics side of what you're doing and not worry too much about the nuts and bolts of the actual physics engine. Again, if you're interested in that, by all means, go and have a look. But for our purposes, we're going to talk about physics engines today. When we finish that discussion, we're going to set it aside, assume that the physics engine does what it does, and carry on with our investigation of robotics. Okay, so we'll probably finish that off today, and then we'll move into the history of evolutionary robotics. As I mentioned, this is a relatively early field, so we're going to go all the way back to 1992 when the field started and look at some of the initial experiments and go from there. Okay, any questions about the assignments? So far, so good? Everyone's got PyroSim installed, up and running, hopefully? Okay, awesome. Okay, so what is a physics engine? Let's start with what it isn't. In traditional computer graphics, if you wanted to render a three-dimensional virtual scene, you wanted to simulate some physics in the old days, what you would do is define various characteristics of all the objects that make up your scene, but you would be defining the geometric properties of those objects, the position of it, its orientation in space, the shape of the object, and so on. You would specify where everything is at time t, and then you would tell the computer what the new positions are going to be at the next time step. The computer would render all of the objects at the next time step. And if you got all of the positions correct when you rendered this scene, it would look like realistic motion, like, for example, an object that's placed a short distance above the ground, accelerating towards the ground, and then stopping when it reaches the ground, right? You can do that, but as you can imagine from the little cartoon example here, it's very intensive. So in the late 90s, the first physics engines were created, which gradually replaced this computer graphics paradigm to creating virtual scenes and saying, instead of getting the computer to render the graphics for us, let's get the computer to render the graphics for us, but also figure out the positions of the objects for us. On the right-hand side, we as the programmer are responsible for figuring out positions. Now in a physics engine, it's the physics engine that's going to figure out the positions of objects. How does a physics engine go about doing that? Like before, we're going to define the position and orientation and shape of objects, the geometric properties of those objects. But we are now, in addition, going to specify physical properties of those objects, like the mass and friction properties of each object. You may already have noticed that in creating objects in PyroSim, you don't specify a mass or friction properties for your object. So again, PyroSim, which is a wrapper around ODE, our physics engine, PyroSim is already hiding some of the details from you. There are additional arguments that you can call from PyroSim that will change mass and friction properties. But again, for our purposes as roboticists, we're going to assume that those are default values, which at the moment I think is 1 kilogram per object. And the friction properties, it's relatively high friction. When you create objects in PyroSim, imagine an object that's wrapped in sandpaper. Very, very rough for now. Okay, so we define the geometric and physical properties of our objects. We define how the objects are attached together with joints, which we'll talk about in more detail. When we add joints, we're actually adding constraints on the way that objects can move. They can obviously no longer move independently to one another. They're dependent on each other's motion. Luckily, our physics engine is going to take care of that for us. And then the magic happens. So once we start up the simulator, once we specify everything that exists in the scene, we're going to loop through this process. And the main thing that happens in every iteration of a physics engine is F equals ma, which hopefully, again, you remember from your high school math or physics classes. Force equals mass times acceleration. Our physics engine knows what the masses of all the objects are, because we've told the physics engine what the masses are. We're going to talk about the forces in a moment. We're going to assume that our physics engine also knows all the forces that are acting on all the objects. So by rearranging the terms, the physics engine can calculate at each time step of the simulation for every object what the acceleration of each object is. And since the physics engine knows the initial positions, it can apply acceleration to figure out the new position and the new orientation of every object, renders that, and on we go. That's the basic idea. We're going to elaborate a little on that today. It gets very complicated in different physics engines, but that's the basic idea. So far, so good? Okay. In the little cartoon here, we have an object that is placed a few units above the ground. So of course, there is one force at this point which is acting on the object, which is gravity. So we have our force there, 9.8 meters per second squared. And that gravity, that force, is pulling the object down. So acceleration is pretty straightforward in this case. The object, luckily, accelerates towards the ground and then stops. Acceleration reaches 0 when it reaches the ground. Why doesn't it pass through the ground?
Because they detect collisions and stop the movement.
Exactly. So another thing that physics engines do, which we'll talk about in a moment, is contact detection and resolution. Detection, when are two objects touching one another? And resolution, what should the physics engine do when two objects are in contact? Okay, that's the basic idea. Okay, so what I'm going to do is I'm going to step through a few slides here and touch on some of the different aspects of a physics engine, and I'm going to use some actual C code that comes from ODE. This is stuff that's hidden down deep in the depths of the C++ side of things. Again, I don't expect you to remember all of the code here, but just to sort of show you how this works. When you call sim.start, it starts up this new C process over C++ process over here. The first thing it does is do a little bit of initialization. It creates a couple of variables, one called world, which, as the name implies, is the data structure that's going to contain all the other objects or all the other data structures, the objects, the joints, and contacts, which we'll talk about in a moment. It's going to contain all the other elements of your simulation. It's going to create a contact space, which we'll talk about in a moment. This space contains all the information about objects that cannot interpenetrate, objects that cannot pass through one another. For example, objects in the floor. The floor and any object, that pair, is a pair of objects that cannot interpenetrate. Objects that may be able to penetrate, what are those objects? What pairs of objects in a simulation should be allowed to overlap?
Joints.
Objects that are connected by joints, right? So if we take a pair of objects and those objects collide with one another, usually the physics engine will take care of them and not allow them to interpenetrate, like two objects colliding together. However, if those objects are attached by a joint, obviously we don't want the physics engine pushing them in opposite directions. We want those objects to stay together. So certain pairs of objects in a physics engine, we're going to tell it, these are allowed to interpenetrate, these are not. Those that are not allowed to interpenetrate are in this contact space. The contact group is a separate housekeeping data structure here, which is all of the pairs of objects that currently are in contact with one another. And there are certain things that the physics engine is going to do with those. We can set gravity. We can set that to Earth gravity. We can set that to Mars gravity. You can turn gravity off, and you can simulate robots in space. You can do all sorts of things. There are a bunch of other nitty-gritty details, which in the reading today, you can go and have a look in the ODE user manual about all these sorts of things. These are setting sort of global properties about friction and other things that happen in the physics engine, kind of housekeeping things. We won't worry about those for our purposes today. Okay. If you send objects across from PyroSim, this is what happens. First of all, we're going to create a body. So on our side, we're going to refer to these as objects or bodies. In ODE, they're known as bodies. And we're going to create a separate data structure for each body. And we're going to assign, as I mentioned before, various physical properties. We're assigning the mass to this object. It's going to be 0.2 kilograms. We can set a density. And we're going to set the distribution of mass within that object. That's what the 111 over there represents. This is otherwise known as an inertial tensor, but we're not going to get into that depth of the detail. But if you really want to get into the nitty-gritty details, you can alter the distribution of mass within an object. Perhaps you create a box in which there are some objects that aren't simulated, but they're inside the bottom of the box. So you might want to make the bottom of the box a little bit heavier than the top of the box. For our purposes, we're going to assume that all objects have equal density within them. The mass of that object is distributed equally throughout the object. Okay. We're setting the mass, and then finally we're setting the position of the object, and we'll continue on with this example of placing an object 6 meters above the ground. What other elements of a body are missing here? We need to set some of the physical properties and the geometric properties of a body. Some important ones are missing. Shape is missing.
The orientation.
The orientation. So we're missing shape and orientation, which are geometric properties of the object. This is a little non-intuitive. In this particular physics engine, there are 2 separate data structures associated with one object. One of those data structures is the body, which deals with the physical properties. And the next one, I'll just skip ahead here, is the geom, or geometry. This is going to specify the shape of the object. There's a reason why ODE separates physical and geometric properties into 2 different data structures. Let's back up for a moment. We mentioned orientation. We just set the position of the object. How do we set the orientation of an object? Well, if we have an object existing in 3-dimensional space, obviously we need to orient it in space. This is kind of a tricky thing to do. The way we're going to do it in this course is we're going to just use 3 numbers, which I think are R1, R2, and R3 in PyroSim, or is it N1, N2, and N3? We changed it somewhere along the line.
It's N1 for joints, and it's R1
for objects. Okay, so R1, R2, R3. I want you to think about R1, R2, and R3, which here is X1, Y1, and Z1. A little confusing. Doesn't matter. We have 3 numbers. Those 3 numbers are going to specify a vector, and we're going to lie the long axis of our object along that vector. That works well for cylinders, because obviously if you place a cylinder long axis along a vector, that cylinder is radially symmetric along its long axis, so we're done. If we wanted to place a rectangular solid along that 3-dimensional axis, those 3 numbers are not enough, because if this is our vector and we place this object here, do we mean this? Do we mean this? Do we mean this? We need a 4th number, which is the orientation or the rotation of that object about this vector. So we really need 4 numbers if we want to completely specify the 3D orientation of an object in 3-dimensional space. To do so, we typically use quaternions, which you see up in the top right here. Again, quaternions can be a little non-intuitive if you haven't worked with them before. So PyroSim is going to hide that detail from you and just require 3 numbers rather than 4. The cost that we're going to pay for doing that, for simplifying things, is that it's hard to place a rectangular solid arbitrarily in 3 space. As you'll see as you build up your robots, we're going to mostly use cylinders, which makes things a lot easier. Again, if you're interested in quaternions and orientation in 3 space, you can dive down into the code and play around with those at your leisure. Okay. So again, let's come back to the geom now. We're going to create a geom, and we're going to create, in this case, a box. And we're going to then associate those 2 data structures together, the geom and the body. We're going to attach them together. And we also specify the orientation of the geom, which is the final piece that's missing. So now we have the shape. We're telling the geom that it's a box, and we've finally set the orientation. And now we have all the information we need about our object. We have its mass, we have its density, its mass distribution, we have its position, we have its shape, and finally its orientation. We have everything. Okay, so why do we have a separate geom and a separate body? You can think of the geom as a skin that is wrapped around the body. And one of the most computationally intensive parts of a physics engine is dealing not so much with F equals ma, that's actually relatively easy. What's much more computationally intensive is keeping track of where all the objects are and whether they are in contact with one another or not. So what ODE does is sort of forget about the body temporarily during this loop, focus just on the geoms of the objects, and figures out, again, which of them are in contact with one another. Why is contact detection and resolution more computationally intensive than F equals ma?
Does it run O of n squared?
It runs of O of n squared, where F equals ma runs of O of n. So for those that aren't familiar with O notation, it's a sort of shorthand in computer science for saying how computationally intensive does something get as whatever it is we're trying to compute gets more complex. And n is going to represent that complexity. In our case, n represents the number of objects that exist in your virtual environment. Pretty straightforward. As n goes up, we obviously need to look at every pair of objects and determine, yes or no, are they in collision with one another. So let's look down here. Let's assume we have 9 objects in our scene, and we need to look at each pair to determine whether they're in contact with one another. How many contact detection events do we need to carry out? Sorry?
81.
Not quite 81. We've got 9 objects. 72, possibly, right? So we visit each of the 9 objects, and for each object, we look at the other 8 and see whether that object is in contact with one or more of those 8 other objects. 9 times 8 is 72. We can do a little bit better than 72. How so?
9 factorial.
Not quite. Let's stick with 72. That's the upper limit, right? We could visit all 9, and for each of those 9, look at the other 8 and tell whether they're in contact with one another.
For pairs, if I'm touching you, then you're touching me.
Exactly. So if I'm touching you, you're touching me, so I don't have to do all 72. I don't have to look at object I is in contact with object J, and then later look to see if object J is in contact with object I. I already know. So we can divide it in half, right? 36. Okay. So you can see then where the n squared comes from. If we have n objects, for each of those n objects, we need to look to see whether it's in contact with any of the other n minus 1 objects. We can divide by 2, but we still have this n squared term in there, which means as the number of objects go up, the amount of computation your machine has to do goes up quadratically. You already know how to create objects in PyroSim. You can place send object or send cylinder in a loop. and you can loop through and send as many objects as you want, and depending on your laptop, you can send 10, you can send 100, some of you may be able to send 1,000. I doubt any of you have a laptop powerful enough to send 10,000. At some point it will crap out because it's too expensive for your computer to do. So the limiting factor in terms of computational requirements for the physics engine is usually contact detection and resolution. Okay, I mentioned before this idea of, let me just back up here for you. I mentioned this idea of spaces before. Why do we have this contact space? This is an additional detail, which is an attempt to try and reduce this. We can never get away from n squared, but we can maybe do even better than 36. How can we do better than 36? Well, we might tell the physics engine to place different objects into different spaces. What are different spaces? Well, the different spaces represent that most of the time in a complex scene, you're going to have hierarchical groupings of objects. So there's certain objects that are usually going to be near one another, and those you're going to have to spend a lot of time looking to see whether they're actually in contact with one another. And then between the groups, there are situations where they may rarely come into contact with one another. In a robotics context, when do you think that's true? When do we have sort of hierarchical collections of objects?
When you have multiple robots in a single simulation.
Exactly. So for any of you, those that decide to tackle swarms in your final project, then contact spaces is going to become your friend. Imagine that the 4 objects on the left there make up one robot, and the 5 objects on the right there compose another robot. Obviously, those 4 and those 5 are always going to be close to one another, because subsets of those objects may be connected by joints, which keep them close to one another. But depending on how the 2 robots move, they may or may not come into contact with one another. So we can break this down into a hierarchical computation where we consider all pairs within spaces and then wrap one big skin around each space and see whether those spaces collide with one another. As long as those 2 spaces do not collide with one another, then we know by definition any one object in one space is not in contact with any object in the other space. Right? Makes sense. If those 2 spaces do collide, what does the physics engine have to do in that case?
Pair all the objects inside.
It's got to go back to our 36 computations. If they don't collide, how many collision detection events does the physics engine have to consider?
0 since they're all connected by joints.
It could be 0 if they're all connected by joints. Let's assume in this example here that it's only a subset of the objects inside a space that's connected by joints. So let's say, for example, consider these 4 cylinders, which are my 2 upper arms and my 2 lower arms. Obviously, they are connected by joints, but my 2 lower arms are not connected by joints. They're connected by a sequence of joints, but they're not directly connected. So if they come into contact with one another, I would like the physics engine to detect that collision and resolve that collision. So we still are going to need to do some computation. How many events do we need to consider?
19.
19? How did you get 19?
It would be 10 for the one on the right.
10 for the one on the right, so we have 5 objects multiplied by 4. 20 divided by 2 is 10.
8 for the one on the left, and 1 comparing the 2 boxes.
Okay,
Oh, 6.
close. Actually, did I get that right?
Wait, 4 times.
3
oh,
times.
No, that's right.
3 times 2 on the right, right? Divided by 2 should be 3, actually.
Wouldn't it would be on?
It doesn't consider the collision between the pairs of spaces in this case.
Oh, okay.
Sorry, my bad.
Oh.
All right, 13 in this case. Much better, right? So you can see if we, again, assume that we have a hierarchical collection of objects, we can use these contact spaces to make things a little bit easier on the physics engine. All right, a lot more detail than we'll probably need for most of the assignments, but just so you have a feeling for what's going on under the hood. Question?
So is this just for like when you have like a shin and a thigh, and I mean If they're jointed, are they technically not colliding, or do we have to specify?
If they're connected by joints, we're going to tell the physics engine to ignore the collision, and we haven't come to that yet, but we will get there. For most purposes, objects that are connected by joints, we're going to tell the physics engine, don't bother considering
we
that.
have to explicitly say that, otherwise it would try.
It's said already explicitly for you
Okay.
in here. You don't have to. Okay, let's move on. Okay, so let's come back to joints. Again, we've talked about this a little bit. We've created our objects, which are made up of the body and the geom data structure. We then are going to create these hinges. And again, what's happening on the C++ side is not that different from what you're specifying here. We create a hinge. In this case, a hinge is a particular type of joint. You'll see in the reading for today that there are lots of different kinds of joints we can create. One thing that all joints have in common is they restrict the relative motion of two objects. So, as we just said before, if we have an object in three-dimensional space, it can have an arbitrary orientation in space. And there are also 6 directions that an object can move: X, Y, and Z. Did I get that right? X, Z, and Y, right? So the 3 linear directions of motion, but of course an object can also rotate in space. It can rotate about the x-axis, the y-axis, and the z-axis. So what the physics engine is really doing when it computes F equals ma is it's computing 6 accelerations. How much the object is accelerating along the x, y, z, and y direction, and how much it's accelerating about the x, y, and z direction at any one time. If we take 2 objects and we connect them together with a joint, that changes the F equals ma computation. So now the acceleration is being restricted by the joint. So it may compute, the physics engine may compute that this object is supposed to move or accelerate in this direction, but if it's connected by a joint, it's going to restrict that particular acceleration. So what joints do is reduce the relative motion and rotation of objects. Okay. Different joints restrict them in different ways. We have a hinge here, which obviously allows the objects to rotate relative to one another, but not move apart. You can create a linear actuator, which is like a piston, and a piston is almost the inverse of a hinge. A piston allows 2 objects to move relative to one another along their long axis. 2 objects attached by a piston cannot move along the other 2 axes, and obviously they can also not rotate. Yeah? Different joints reduce relative motion between objects in different ways. Okay. We need to give, in the case of the hinge joint, an anchor about which the 2 objects are going to rotate. And we talked about joint normals or hinge axes. It's the same thing here last time, right? The normal is a vector that defines the orthogonal plane through which the 2 objects rotate. Okay. So let's come back to contacts now. This is kind of interesting. What we've talked about so far is the physics engine iterating through this loop 100 times, 1,000 times, however many times we tell it to do so. During this loop, certain events may occur. So the C++ code is also event-driven, and some of you may or may not have experience writing event-driven code before. What happens in event-driven code is that the code runs as usual, but if there is an event that occurs, and we define what those events are, the program will jump to a particular function that's been defined to handle that event. So inside the C++ code, there is a callback function, and that the name there is a reminder that when a particular event occurs, call back to this function, and this function will deal with that event. What is the event? The event is that the skins wrapping 2 objects, 2 geoms, are near one another. They're not touching. We don't know that yet, but we know that they're near one another. And what exactly near means gets a little complicated, but we'll assume that the physics engine says there are objects that are close enough that I should probably look to see whether they are in contact or not. Objects that are far, from the point of view of a physics engine, it ignores even considering whether those pairs of objects are in contact with one another, which again helps us with this expensive computation. Okay, so suddenly this function is called. These two geoms are near one another. What do we do about it? The first thing we do is we collect the two bodies associated with those geoms. Remember, we have an object, and an object has two data structures associated with it. Body, which specifies mass properties, and geom, which specifies the geometric properties. We want the two bodies. And then, if you're familiar with reading C++ code, we're asking to see whether those two bodies exist. We won't worry about that detail for a moment. There are situations in which we have geoms but no bodies. For our purposes, I don't think that's ever going to happen. We have these two bodies, and then we can ask, are these two objects connected, excluding a particular type of joint? This gets a little confusing. So I mentioned we have hinge joints and we have linear joints or linear actuators like pistons. There's a third type of joint, which is a contact joint. This seems kind of strange. Imagine we have two balls and they are moving towards one another in the physics engine, and suddenly they do collide. The physics engine detects it and is going to resolve this contact now. It's going to make sure, it's going to deal with the fact that these two objects are in contact. What should the physics engine be doing once it knows that these two objects are in contact with one another? They weren't at the previous time step, and now they are. What does the physics engine need to do with the situation?
I mean, I'm assuming it needs to like know the velocity of each object in the friction and calculate like which direction to send each ball.
Which direction to send each object, exactly, right? These objects cannot continue on with the acceleration path that they were following because they're now in contact with one another. So the physics engine is going to apply some additional forces that is going to change the acceleration. We're going to change F, which is going to change the F equals ma calculation. It's going to apply forces which are trying to push the objects in the other direction. Depending on the friction properties and the previous acceleration of those objects, that's going to determine how much the physics engine is going to force the objects apart.
Is elasticity a part of this physics engine?
Elasticity is also a part of that. So do we have two ball bearings that are coming into contact with one another, or do we have two beach balls that are coming into contact with one another, right? There are very different ways in which those two pairs of objects might respond to a collision event. Again, PyroSim hides most of those details from you, but you can go into the C code and play around with that if you like. Okay, so how is it going to apply these additional forces? What the physics engine is going to do is temporarily create a joint between this pair of objects, a special type of joint, not a hinge joint, not a linear joint, but a contact joint. And that joint is going to exist for just one time step. It's temporary. These objects suddenly have a joint attached together. And as I've already told you, what all joints have in common is they restrict the relative motion of connected pairs of objects. Makes sense in this case. What kind of motion are we restricting? Further interpenetration of the objects. That's why contacts are considered joints in a physics engine. Okay, so what we're asking here, we're saying there are two objects which are near one another. We're asking, are they connected by a joint? But if they're connected with this joint, we don't mean that kind of joint. Are they connected with a hinge? Are they connected with a linear joint? If so, return. Forget about it. So we're leaving the callback function. So the event was triggered. These two objects are near one another. My lower arm is near my upper arm, which triggers this event. I go inside this function and I see that B1 and B2 are connected by a hinge joint, so return. Don't do anything else. They're supposed to be near one another. Next time step, another event is triggered. O1 and O2, B1 and B2 are close to one another again. Ignore, ignore, ignore. B1 and B2 are near one another. They are not connected by a joint. So do not return. Continue on into the callback function, and let's see what we should do next. So we continue on. At this point, what we're going to do is try and approximate the area in which the objects are coming into contact with one another. If we have two spheres which come into contact with one another, what can you tell me about the space in which they collide? Could be a point if they are two ball bearings. If they're a beach ball, it may be a small circle which represents the point at which they're pushing up against one another. Depending on the shape of the object and the material properties that we define, which we haven't really talked about yet, that surface may be very simple, like a point, the simplest possible collision region you can imagine, but it could also be more complex. If we have two cubes that come into contact with one another, if they had hit each other side on, like you see here, perfectly side on, then we know what the collision region is. It's the shared sides of the two cubes. Is that the only possibility? How many possibilities are there?
I guess it's almost infinite because they can come at different angles.
Exactly. They can come at different angles, different orientations. Remember, they can have different orientations in three-dimensional space. There's lots of different ways in which two near objects may actually be in contact with one another. So different physics engines approximate the collision region differently. In the case of ODE that we're using here, we're going to sprinkle a bunch of point contacts near where the two geoms, the two shells, are closest. So it's going to compute the two shells around the objects, look to see where those shells are closest, and sprinkle a bunch of points. And we can play with how many points we use. As you could probably figure out by now, the more points that we tell ODE to use to approximate that collision region, the more accurate the physics engine is going to deal with that collision event. Okay. So and again, that's all set for you. We hide that for you, but you can go in and again have a look. For each one of those points, one or more of those points may actually lie in the region. So if those points happen to lie inside the shell of O1, and that point also lies inside the shell of O2, that point says, I'm here. I'm within the region in which the two objects are currently overlapping. The more points that speak up and say we are in the region of collision, as well as we can tell, the more those two objects are in collision with one another. Okay. We can also tell those points to sort of approximate that collision in different ways. So you can see bounce here, and mu equals infinity. Mu is a friction parameter, which is set very high. Remember that all the objects, for our purposes, we're going to assume they're wrapped in sandpaper. So if two objects attach one another at an angle, they don't hit each other side on, then obviously two objects that are wrapped in sandpaper, they're going to slow each other down much more than two balls of ice would if they hit each other side on. They will slide past one another. The amount of slide is represented by this mu property here. The amount of bounce, as you can imagine, has to do with, are these ball bearings or beach balls that are colliding? Okay, so we compute for a bunch of these points, these different properties, and then we ask if there is, and I won't get into the details, but if there is at least one of these points that has its hand up that says, yes, I'm in an area of overlap of these two objects, we are going to create a contact point. So at exactly that point, the point that put its hand up, we're going to assign a joint to those two objects at that point. The position of that joint is right there, and we're going to attach that contact joint to the first body and the second body. We're attaching that contact to the two bodies rather than the two geoms, rather than O1 and O2. Why are we attaching the contact joint to the bodies rather than the geoms?
Do they have the data needed to calculate the force?
The forces, right? Remember that the physics engine is going to use these contact joints as forces. Wherever there is a point, and we may be attaching more than one contact joint at one time step to a pair of objects, there are forces that are going to be applied at exactly that point, which is going to apply forces in the opposite direction to the current acceleration of the objects. If the two objects hit each other straight on, then it's going to apply forces at that point pushing in the opposite direction. If they hit side on, then there are forces that are going to push in the somewhat obliquely. Right? So again, it gets complicated depending on the shape of the object, their accelerations, and the relative position at which they hit. For our purposes, we're approximating this by sprinkling points, and those points are going to start to generate opposing forces in this time step. The next time step, which we'll get to here, the next time step here, we're going to throw away all the contact joints. They're gone. We go through this loop, we start this loop again. If those objects are still in contact, we're going to sprinkle a new set of points, apply new forces, and on we go. Question?
So in the previous slide, if there's multiple, so it's triggered by a point reaches a certain threat or value where it has to have a repercussion force. But if there's multiple points, can they then have somewhat counteracting?
They may. So again, it gets complicated, right? So again, we're sprinkling these points within the region of overlap of the geoms of the bodies. Each one of those points, depending on where it is and actually depending on the properties we've set for it, they're going to apply different forces. What does the physics engine do? Well, I haven't got a chance to say this yet, but what it's really going to do is when it computes the new accelerations for each object, it's summing up all of the forces that are acting on each object. So let me just skip ahead, actually. Maybe it's easier to do it here. Here's the master loop that exists inside the C code here. This is the loop that's repeated 1,000 times if you tell your physics engine to run for 1,000 time steps. And this line right here, dworld step, this is where all the magic happens. Inside that function call, down in the depths of ODE, it visits each object in turn, looks at all of the forces that are acting on each object. So if an object is above the ground, one of the forces we know is the force of gravity that's pulling it down. If that object was in motion in the previous time step, it has some momentum, which is a function of its mass, which means there's also a force pushing it in the direction it traveled in the previous time step. If it's in contact with other objects, if there are these contact joints, those contact joints are also contributing additional forces to that object. We sum up all of the forces. Those forces are all vectors, so we're summing up a whole bunch of vectors, which gives us one final vector, and that is used to compute, to divide by the mass, which gives us back a new vector, which is the acceleration of the object. That new vector, the acceleration vector, how many numbers are in that acceleration vector? How many numbers do we need to specify the new position and orientation of the object? 6, right? So it's the acceleration along x, y, and z, and around x, y, and z. Does that answer your question? Okay. All right. So that's what's going on in the center here. Let's go back to the top of the loop here. So here we go. At the beginning, we're going to call this d-space collide. And when we call this function, it's going to trigger 0 or more events. And an event is if there are a pair of geoms that are near one another. If one or more of those events are called, then the code jumps here temporarily, sprinkles all the points, comes back to this line, leaves this line. You can pause your simulation, and you'll get to that later in the assignments, and you can step by step through the simulator. Assuming that the simulator is not paused, it will change the positions and orientations of all the objects. And you'll notice this argument here, 0.05. This will become very important to you later on when you're creating complex simulations. This is the step size, or the amount of time in seconds that pass between one instant of time in the simulation and the next period of time, the next instant of time in the simulation. From our point of view here in the real world, time is continuous. From the point of view of your robot or any objects that exist in the physics engine, time is not continuous, it's discrete. I was here, and then suddenly 0.05 seconds later, I'm here. Then I'm here, then I'm here, and so on. This is important because, again, remember that your robot is sensing its environment, so it's sensing at discrete intervals. If you get a value back from a sensor, and then you look at the next value of the sensor, that's the value of the sensor at 0.05 seconds later.
When you use the time step to compute the next iteration of the world,
Yes.
if you change the time step, would the amount the world change, or does the world change by a fixed amount each time? Like is like the delta of like everything in the world fixed through time in this case?
That's a very good question. So what happens if we change the time step, right? Do objects move more or less if we change the time step, or do they move the same amount regardless of what the time step is?
Yeah, but now we just have more updates.
Possibly. Let's think about this, right? So now we're going to have to bring in some units. We have 0.05 seconds. That's the amount of time that elapsed from one time step to the next. Remember that the physics engine, the currency of the physics engine is accelerations, right? The accelerations are measured, for our purposes, in meters per second squared, right? So if I decrease the time step, let's say we have the time step from 0.05 seconds to 0.025 seconds, what happens to the relative positions of the objects? Do they move more or less?
Shouldn't they move the same distance? It's just you have a smoother motion rather than like at least
Overall, the objects might move the same amount, but we're thinking about how much the position of an object changes from one time step to the next time step. The object was at this point at t0, and now we want to think about the new position of the object at 0.05 seconds later.
but it moves less.
Move less, right? It's meters per second squared. If we're reducing the amount of seconds from 0.05 to 0.025, then the amount of meters is going to decrease. Acceleration is still the same. Whatever the physics engine computes, regardless of the time step, it's still the same acceleration. But the physics engine, the final step, when it computes or draws the objects, it comes up with a new position. It's going to use the acceleration and look at the time step, right? And the time step is going to dictate how much of the position changes according to the acceleration.
How much error is introduced? Because to get position, you have to integrate twice from acceleration. So is there, what amount of error is introduced?
That's a very good question, and it depends on the way in which the physics engine is performing the integration, which, if I remember correctly, is RK4. And those that know about integration, that's not a very accurate way of doing things. But you can counteract that, the fact that it's doing sort of a sloppy job of computing F equals ma by doing what? What can we alter here to make our simulator more accurate?
More time steps.
Not necessarily more time steps. If we add more time, so the number of time steps, the default is 1,000. We could do 2,000. That just means that the simulation will run for longer, not necessarily more accurately.
Smaller value for the
Smaller time step, exactly. So the reason we're spending so much time talking about this one number is that this is the most important number in your entire physics engine, and it's probably going to become the most important number in your final project. Getting that number right makes all the difference between an accurate and inaccurate simulation. The smaller we make that number, the smaller the change in position from one time step to the next, and the less error that can creep in during the integration that's performed in the F equals ma calculation.
So if you had like a really big time step or an object going like super fast, is there a risk of missing the collision?
Absolutely.
Yeah.
So if you set the time step high and you shoot two bullets at one another in the physics engine, which you can do, you can get situations where they pass through one another. If you ever see non-physical behavior in your simulation as you continue through the assignments, and I guarantee you, you will, first place to go look is the time step. So if reducing the time step makes our physics engine more accurate, why don't we just reduce it to 0.000001?
That's a lot of more computation.
Exactly, right? Remember, every time through this loop, we are asking the physics engine to do a certain amount of computation for us. If we reduce the number of time steps, then we are increasing the amount of work it does, as long as we're also increasing the number of time steps.
Also, if we want our simulation to simulate like the same amount of like stuff, wouldn't you also have to increase the number of time steps you want it to run in proportion to
Exactly.
change?
That's it, exactly. So if I want to simulate 1 second of physics, right, then I need 1 over 0.05 number of time steps, right? So that'll give me whatever that works out to be, that many 0.05 seconds carried out. By the end of the simulation, I've simulated 1 second. If I have the time step to 0.025, then I need to double the number of time steps. I have to double the number of times I iterate through this loop to still simulate 1 second of real time. You can play around with this. You can simulate 1 second of physics on your machine by setting the time step to be 0.00001 and doing a million iterations of this, and it'll take more than a second on your computer to simulate 1 second of physics. And that's an important point, so I just want to pause here for a moment. The amount of time that passes in your virtual world can be different from the amount of time that passes in the real world, which is wall clock time. Depending on the number of time steps you set and the step size, it can take longer to simulate your virtual physics than it does for that time to elapse back here in the real world. If you set the time step relatively high, so you have a relatively inaccurate but fast simulator, because you can reduce the total number of time steps, 1 second can elapse much faster in your virtual world than it does back here in the real world.
Is there any support in the engine for an adaptive time step that sort of shifts based on, oh, interesting things, I better ratchet down?
There absolutely is. I forget the command, but you can actually comment out deworld step and replace it with that adaptive time step, which again it works okay for some things, not for everything, but that's a good point. There is an entire field dedicated to physical simulation. As you can probably tell by now, it gets really, really complicated once you start to get into the details. A lot of work still going on today is how to reduce this given what's going on in the simulation, and also how to adaptively set the time step based on what's going on in the simulation.
So, do you give us a method in Python to modify this, or do we have to go modify it in the C code?
Yes, so when you call, I think it's when you call start, you can set dt equals. It's either in there or it's in the constructor when you create the simulator. I don't remember. But you can actually set dt equals. And you can set it to different values and run your simulation, and you will definitely see the difference. If you set dt high, you can see big jumps in the relative positions of your objects, and your simulation will finish before you've even watched it. Set dt very slowly, the motion will be much smoother and will take much longer. It'll look like everything is running in slow motion. It's not in slow motion. From the point of view of the objects inside that virtual world, time is flowing just as fast as it always does. Okay. What was the dt for the Matrix in the movies? Did time run faster in the Matrix or slower than the real world? Go back and watch the movies and see if you can figure out what dt is for the Matrix. Okay, so we compute all the accelerations and then the new positions and orientations for our objects. We throw away any contacts if they exist. And then the last thing we do before we finish this iteration through the loop is draw all the objects. Later in the assignments, you're going to actually turn off the graphics. And if you do, this still loops through. We still do all of our physics, but we just don't draw the objects. This is computationally intensive,
and the draw routines are a close second. So if you turn off the graphics, you will see that your simulation runs much faster than if you actually draw the graphics. So once things get a little more complicated in the assignments, what you're going to find yourself doing during the debugging phases is leave the graphics on, watch your robot, make sure it's doing what you expect it to do. Once you've worked out all the bugs in your code and you want to let the simulation really do its thing, you will play blind. There's a setting you can set that will basically turn off the graphics. And if it took 5 seconds to watch your simulation, for most of your laptops, when you turn off the graphics, it'll usually run 5 or 10 times faster without the graphics. So far, so good? All right, there's the master loop. You tell the C++ code how many times you want to iterate through this loop and how much time should elapse during any one pass through this loop. Any questions about that before we move on?
Could there be, I didn't see any support for a think quickly in the engine, but I only want to see every 50th time step on the screen. I didn't see a
You can do that. I don't think that's set up in PyroSim at the moment, but again, you can be clever where you say, we're only going to draw the objects every second frame or every 10th frame, but we still want to do the physics every frame. You can do that, which will also accelerate things to some degree.
Stop motion sort of.
Exactly. I think you can probably go in the C++ code, and if you know how to alter it and recompile it, you can do that yourself. Yeah. I don't think it's available on the PyroSim side yet. It's either all or nothing. Question.
So if you wanted to accelerate your simulation, you stop doing draw calls, makes it run faster.
Yes.
Also, when you do draw calls, in order for it to make sense to us, like, I'm sure it runs at like a certain frame rate, unless it's just like, oh, every physics engine time step, draw a new frame.
There's no pause. It's running as fast as it can, depending on the time step, the amount, the size of the time step. It's not waiting for you. It's got plenty to do without requiring any sleep calls.
All right.
Yeah. Any other questions? Okay, let's move on. Everything we've talked about up till now is physics, right? We haven't said a word this morning about robots. One of the other things that PyroSim does for you is put additional code on top of the physics engine to simulate those objects which are above and beyond objects and joints, the other building blocks of robots that we need. There are 4 other building blocks that we are going to add on top of the physics engine: sensors, motors, neurons, and synapses, right? Okay, so how does PyroSim do that? Well, the sensors are going to exploit, they're going to piggyback computations that the physics engine is already doing. One of the sensors that you can give your robot are the touch sensors. So let's assume we have this little cartoon quadruped robot. We're looking at the quadruped from its right side. There's its front right leg here and its back right leg here, and assume that we placed a touch sensor in each of the 2 legs, and there's some object there in front of the robot. The robot doesn't know about the object because it doesn't have any sensors to sense the object yet. The only thing it knows is, are the touch sensors firing or not? How do we compute that? Well, in order to simulate the touch sensors, we piggyback on the near callback function. Remember, the near callback function, as the name implies, is going to be called back. It's going to be called into operation when 2 objects are near one another, like, for example, the back right leg and the floor. In this case, the back right leg and the floor are in contact with one another. The physics engine is going to sprinkle some points, and if one of those contact points puts up its hand, we set the value of the touch sensor to 1. The front right leg is near the ground, which again triggers the near callback function. In this case, none of the sprinkled points put up their hand. That object and the ground are near one another, but they are not in contact. No points put up their hand, so we set that touch sensor to 0. The object is not on the ground. All other objects, if they did not trigger the near callback function, we set, if they have a touch sensor inside of them, we set their touch sensor value to 0. So we're adding a little bit of additional code on top. We're constructing this touch sensor data structure, which again is hidden in the code here. You don't have to worry about it. But we're using stuff that the physics engine is already doing to simulate, sensors. Question?
If the sensor is, say, at a specific point on the object.
Yep.
And the object is in contact with another object, but that point is not in contact with the other object?
Yep.
How is that resolved?
We assume that touch sensors detect any collision anywhere on the surface of the object. Imagine your object is covered in some electroactive skin, and any touch on the surface of that skin is reported back to the touch sensor. You can't localize the touch sensor to any one part of the object, unless, for example, you were to add a small object on the end of the leg, call it the foot, and then put the touch sensor inside the foot. So if you want a touch sensor that is much more specific, you do it by creating a smaller object and putting the touch sensor in there.
So the touch sensor is just like an abstract way of saying, look for collisions on this face of this object.
Exactly. That's what we're doing on this side. For our purposes on this side, if you embed a touch sensor in an object and you get back the sensor data, you're going to get back a vector of 1s and 0s, whether the touch sensor fired or not, right? We're hiding the physical instantiation of that sensor from you. Other questions? Okay, there are a number of other sensors that are available to you in PyroSim, like, for example, the light sensor. Remember the robot that grabbed the blue object and lifted it onto its back? We assume that that blue object had was a light source. So let's assume that this square object in front of it is a light source. It's emitting a light. And we're going to place a light sensor inside the object here, or on its back if you want. How would we simulate a light sensor, given what I've told you about ODE so far? Someone's calling in the answer.
Probably like a vector field or something like that.
A vector field, maybe we could do that. Simulating vector fields are very computationally intensive because we need to visit a whole bunch of points in the three-dimensional space of our physics engine and compute things going on at those points. Very computationally intensive. We could do it that way.
It's like a double, where it's like 0 is no light and 1 is all light.
We could do that, so we could assume that our light sensor is going to be binary, that light intensity above some value triggers the light, intensity below some value means the light is turned off. But how do we know what the light intensity is that's touching the robot?
Proximity.
Proximity, right? Generally speaking, the closer the light sensor is to the light source, the more light intensity there's going to be at the light sensor, with one obvious exception. If there's something in the way, occlusion, right? Let's assume for our purposes this morning, we're just exercising our growing intuition about physics engines. Let's just ignore occlusions. We're going to cheat and say the closer the light sensor is to the light source, the greater the light intensity that's falling on that light sensor. We're not going to assume a binary light sensor for a moment. Let's assume a floating point value. 0 means complete darkness, and an infinite value means I'm in the heart of the sun. It's really bright. Okay, so we've got our light source over there. Let's assume our robot is moving, which means obviously the light sensor is moving, which means obviously the proximity between the light sensor and the object is moving. How does that value, that one floating point value, change as we approach the light or move away from it? What's the specific relationship? Again, back to high school physics.
Inverse square law.
The inverse square law, thank you very much. Okay, so the amount of light that's falling on an object is inversely proportional to the distance of that object. If you pick a bright light and you start moving towards it, From your point of view, it's definitely getting brighter, but it's not getting brighter linearly. If you have your distance to a light source, the perceived amount of light is actually 4 times what it was before, which I realize is a bug in PyroSim, and hopefully this has been fixed by one of my students by now. We'll see. Here's 3 lines of code that was originally in there to try and simulate a light sensor. We take, we calculate the position of the object in which the light source exists. So there's some code in there that says, I'm a light sensor and I'm in object 1. So we get the position of object 1 inside the physics engine. At any point in time, you can ask for the position, orientation, velocity, acceleration of an object. You can query any of the properties of an object at any time. We get the x, y, and z position of the object. We have told the physics engine that object 4 should be treated as a light source. So the physics engine says, aha, okay, you want the position of object 1 and the position of the light source. We then take the Euclidean distance between those 2 objects. We got the 1 over d correct, but it should actually be 1 over the Euclidean distance squared. If a light sensor ever manages to reach inside the box and overlap exactly the center of the box, then the light sensor is in the heart of the sun. Distance is 0, 1 over 0 is infinite. Luckily, thanks to collision detection and resolution in the physics engine, that never occurs. Yeah? If the distance between the robot and the light source is infinite, 1 over infinity is complete darkness. Right? That's more or less how we simulate a light sensor.
Would this break if you had a glowing robot, for example?
Ah, interesting. What happens if we put a light source on the robot? You can do that in PyroSim. Give it a try. Get back the sensor data from the light sensor and see what the light sensor tells you. Yeah? You can create different scenes, obviously, in PyroSim. Place different objects and different sensors where you want. Figure out for yourself how it operates. Okay, if you're interested in physics engines, it's interesting to sit down and think about some of the other kinds of sensors that might exist. Another important sensor that we'll see many times in this course is an accelerometer, which gives information about the orientation or acceleration of the robot. Obviously, that's very important. We have 2 of those sensors. They exist in your inner ear, which tell you something about how your head is oriented relative to gravity. And if you spin around really quickly and get dizzy, that's because you're fooling your 2 accelerometers in your inner ears. Okay, so as you can see, we're now starting to layer additional code on top of the basic physics engine to help us build and simulate robots. So we've got sensors locked down. What about motors? Let's have a look at motors. As you might guess, motors are always attached to joints, and motors apply a force to the joint. The joint then applies forces to the pairs of objects that joint connects, and then the physics engine takes over, right? Remember that the physics engine is always summing up forces and figuring out the new accelerations of the objects. So let's go back to our cartoon quadruped here. Let's assume that at this point in time, the right upper leg is slightly off the ground. And let's assume that we have a motor that is sitting on the hinge joint that connects the right upper arm to the main body. This is how we do it. So if you send across from your code, if you add a motor to your simulation, we're going to apply that at a hinge, and we're going to have to alter the hinge a little bit. We're going to do that by setting a particular parameter of this hinge, which is the total amount of force that can ever be applied at that joint. We're going to be applying forces, and we want to make sure not to break our physics engine, so we're going to do that first. We're then somehow going to have to tell the motor what the desired angle of the joint should be. That's what the motor is ultimately, or that's what we need to start to simulate the motor. The input to the motor is a number, which for our purposes is going to be desired angle. The output of the motor is force that's applied to the joint. Desired angle in, force out. Okay. We're going to assume in everything we do here that when you create 2 objects and you attach them by a joint, The angle between those two objects for the moment is 0. This is non-intuitive and takes a little bit getting used to. We're going to assume that the angle is sort of the default angle. If I take this object and I attach them by a joint, the angle between these two objects is 0. If I take this object and I attach them by a joint, this default angle is 0. Again, kind of confusing. Non-zero angles are going to be extension or flexion. Okay? Extension is any rotation of an object away from the center of body. So this is extension, this is flexion. If my arm is at my side, this is flexion, this is extension and this is flexion. I'm bringing it in. We're going to assume that positive numbers mean we want the objects to rotate away from the body. Extension. Negative numbers mean we want to rotate the objects toward the center of body. And we're going to use negative numbers to represent flexion. It's kind of arbitrary, but we're going to use that convention for the rest of the course. So we have X, Y, and Z, and positive numbers for extension, negative numbers for flexion. We'll leave it there for today. You have a quiz due tonight. Undergrads, you're working on assignment 3. We'll talk about assignment 4 on Tuesday. See you then.